Hey everyone! Today we're going to take a look at a function with some pretty interesting properties. It's a function that satisfies the intermediate value theorem, but is also discontinuous at every real number. So the fact that it satisfies both of these at the same time is kind of interesting. So the function that I'm talking about is Conway's base 13 function. And it was originally devised by mathematician John Conway to be a counterexample to the converse of the intermediate value theorem. So in order to properly motivate and understand where this function comes from, we are going to spend a little bit of time recapping the intermediate value theorem and the intermediate value property. Then we'll talk a little bit about the converse to the intermediate value theorem, which is going to lead really nicely into our discussion of Conway's base 13 function. And so once we have that motivation there, we'll go ahead and actually define Conway's base 13 function. And then by looking at a specific example, we will show exactly why it is that this function is such an interesting counterexample to the converse of the intermediate value theorem. So without further ado, let's go ahead and get into it. So we're going to go ahead and get started by taking a look at the intermediate value theorem. And the intermediate value theorem at its core is about something we call the intermediate value property. So I have the exact statement of this right here. Before I jump into that though, I want to just make some notes and just kind of give an idea of what the intermediate value theorem is saying before we jump into the exact definition. So this is going to be just some notes on the intermediate value theorem. So the main idea behind the intermediate value theorem is as follows. Let's say that you have a continuous function, and let's say that it looks something like this. So here's a continuous function f. And let's say that we pick some inputs, two inputs. We'll pick an a value here, and then we'll pick a b value, let's say right here. And looking at the graph of this function, I can kind of estimate what the output of the function is for each of these inputs. So when I input a, the output is right about here. So that height right there is going to be f of a. And then for b, when we input b, the output is about right here. So that's f of b approximately. So the idea is, well, at a, the function is at this height, and then at b, the function is up here at this height. And the intermediate value theorem says as long as the function is continuous, then it can't skip over any of the y values in between. The function has to actually hit all of the y values in between here as long as the function is continuous, because it can't really make any jumps. It can't jump over any of the y values without touching them. So that's the idea. For any y value that I pick in here, there's always an x value that's in between a and b, such that f of x is equal to y. So there's no skipping going on, and let me just go ahead and write it like that. So the intermediate value theorem, which I will denote IVT, says that if f is continuous, then it doesn't skip any values between f of a and f of b. It doesn't skip any values between f of a and f of b. And that's it. That's the idea behind the intermediate value theorem. We are going to need to make this a little bit more precise, and so we're going to use this formal statement of the intermediate value property now in order to do that. So let's go ahead and dive into this. The intermediate value property. Let I be an interval, and this can be a closed interval or an open interval, it doesn't matter. A function f from I to r satisfies the intermediate value property if the following holds. Given an a and a b in I with a less than b, and given y strictly between f of a and f of b, there exists an x in the interval a to b such that f of x is equal to y. Okay, so what is this saying? This is kind of the formal way of describing that the function doesn't skip any y values. And I'm going to go ahead and make a new sketch, even though it's going to look very similar to the one we already have. I'm going to go ahead and draw it again anyway, because we're not starting with a continuous function in this case. So what this is saying is that if you have a function And for any a and b like this that you pick, and let's say f of a is here, and let's say that f of b is here. So in that case, we have that this point is on the function, because when you input a, you get f of a. And we have that this point is on the function. Okay. And we say that this function, whatever it is, has the intermediate value property if for any y that you pick in here, you can always find an x value such that f of x is equal to y. And in order for the function to satisfy the intermediate value property, this has to be the case for any a and b that you pick, like this, and for any y that you pick. And then so from our discussion earlier, really all the intermediate value theorem says is that if a function's continuous, it has to satisfy this property. That's what the intermediate value theorem is. And so now with this formal definition, I can go ahead and state the intermediate value theorem. It goes like this. If f from some interval to the real numbers is a continuous function, then f satisfies the intermediate value property, which I will write as IVP. And there is our intermediate value theorem written sort of precisely. Now that we have that, we're ready to look at the converse of this statement and get into the motivation for Conway's base 13 function. Okay, so I have gone ahead and copied down our intermediate value theorem here, and we'd like to start looking at the converse now. So the question that is going to guide our further exploration is about the converse. So we'd like to know, if we flip this statement around, is it still true? So if a function satisfies the intermediate value property, is that function necessarily continuous? So this is essentially asking, is the converse of the intermediate value theorem true? Now the answer to this question, I believe I have already given away, because in the beginning of this video, I mentioned that Conway's base 13 function is a counterexample to this statement. But it turns out that you don't actually need Conway's base 13 function to find a counterexample. So the answer to this question is no, the converse of the intermediate value theorem is not true. And the function defined as follows is a counterexample. So the function is f of x equals sine of 1 over x if x is not equal to 0, and 0 if x equals 0. It turns out that this function satisfies the intermediate value property, and it is discontinuous at x equals 0. Okay, so this is the standard counterexample to the converse of the intermediate value theorem. And this is not really the main function that we're going to talk about, so I'm not really going to dive any further into this. But I just wanted to show you that you don't have to go through the construction of Conway's base 13 function to find a counterexample. There's a simpler one, for example, this one, and there are even more counterexamples as well. If you're interested in what other simple counterexamples there are and how you can find them, I recommend looking up Darboix's theorem. Darboix's theorem is a nice tool that kind of allows you to find other functions that satisfy the intermediate value property, but they might not be continuous everywhere. So, given that there are other counterexamples to the converse of the intermediate value theorem, what is it that makes Conway's base 13 function so interesting if it's not the only counterexample? Well, you can kind of think about it this way. This function, though it is a counterexample to the converse of the intermediate value theorem, it's perhaps not the most interesting counterexample, because really the function's only discontinuous at this one point in the domain, at x equals 0. I wonder if there are some more interesting examples that are discontinuous at more points, right? And this is where Conway's base 13 function is really interesting. So we've come now to kind of the main claim of the video that we're going to eventually try to sketch out a proof for, and that is this. Conway's base 13 function satisfies the intermediate value property, but it is discontinuous at every single real number. So unlike this function, which satisfies the intermediate value property, but it's only discontinuous at this one point, Conway's base 13 function is much stronger of a counterexample than that because it's discontinuous at every single real number. All right, so now I'm sure you're itching to actually see the definition of this function to try and figure out how this all works. So let's go ahead and get to that. Okay, so in order to define the function, we're going to need to first mention a few things about writing down real numbers in base 13. So for this part, I'm going to assume that you are familiar with how to write numbers in bases other than base 10. If you are absolutely unfamiliar with that, you might want to brush up on that before getting to this part of the video. So the first thing is that when we write down numbers in base 13, we are going to use the following digits. So in base 13, we're going to use 0 through 9, so 0, 1, 2, and so on, all the way through 9. And then we need some more digits, which we're going to denote by A, B, and C. So for base 13, we need 13 digits. Those 13 digits are going to be the 0 through 9, and then A, B, and C. Okay, the second thing we need to watch out for is how we represent numbers in base 13. So let me section off a spot up here to make some notes. So you might be familiar with the fact that in base 10, some real numbers have more than one decimal representation. So in base 10, for example, it is a fact that 1 is the same thing as 0.999 repeating. You may have heard this before. So these are two different representations of the same exact number. And the same thing happens in base 13. So there are certain real numbers that have more than one representation. For example, 1 in base 13 is the same thing as 0.CCC repeating. So we have these two different representations. And in the arguments that are going to follow, we want to make sure that we don't have two different representations. So what we're going to do is, whenever I write down a number in base 13, I'm always going to assume that it's not like this. It does not end in an infinite number of C's. It turns out if you throw out those ones, then every real number has just one base 13 representation. So that's the next thing that we need to make sure that we're clear on. Each real number has exactly one base 13 representation that does not end in all C's. And so again, whenever we write down a representation in the future in this video, we're going to assume that it does not end in an infinite number of C's. Okay, so with that out of the way, the definition of Conway's base 13 function has to do with taking a real number input, writing down its base 13 representation, and then sending that number to a certain output based on what the tail of that expansion looks like. So what do I mean by based on what the tail looks like? The idea is this. If x is equal to, let's say, n point a1, a2, a3, and so on. Here, when I write this, n is just an integer, this is the decimal, and then here's a bunch of decimal digits. So there's a few things that can happen with the tail of this. One, x has a tail that looks like a b being this digit, in this base 13 digit, and then some numbers, x1, x2, let's say up to xn, and then a being this digit, and then some more numbers, y1, y2, and so on. With all of these numbers, the x1 to xn, and then the y1, y2, and so on, these are all 0 through 9. So with xi and yi in the set 0 through 9. This is one thing that could happen. There are a bunch of real numbers out there that have a tail that looks like this. Second thing that can happen is that x has a tail that looks like c x1, x2, all the way to say xn, and then a, and then your y1, y2, and so on. Again, with the xi and the yi in the set 0 through 9. These are two options. You just take a random real number and take a look at it. It could have one of these two options. The third option is x has neither of these tails. And together, these three options cover all real numbers. So you take a real number, you write down its base 13 expansion, and either it ends in a tail that looks like this, a tail that looks like this, or it does not end in either of those tails. So just for ease of language as we move on, I'm going to say that if x has a tail like this is a tail of type B. And I'm going to say that this one, x has a tail of type C. Okay, so finally we've reached the point where we can actually define this function. So we're going to go ahead and do that. I'm going to go ahead and erase this part up here. We don't really need this anymore, just so we have a nice open space to define this function. So here we go, definition. Let's go ahead and use a C for Conway for this function. How about? So let's say that C of x is defined as follows. Now I'm going to go ahead and use the same notation that I've used down here. So x is some number, and it either is going to have a tail like this of type B, like this, type C, or neither of those two. So if x does have a tail of type B, then the output of Conway's function is going to be the following: x1, x2, all the way up to xn. Again, each of these x's are digits. This is the integer part. Now I'm going to have a decimal point, so point. And then I'm going to use all of these ones, y1, y2, and so on. This is if x has tail of type B. Okay, and if x has a tail of type C, we're going to do the same thing, except we are going to make the output negative. So it'll be x1, x2, and so on, all the way to xn, point y1, y2, and so on, however far that it goes. And this is if x has tail of type C. And then finally, if x has neither, we're just going to map the value x to 0. And I'm just going to put if neither here. This is the definition of Conway's base 13 function. And one important thing that I do need to note is that these numbers are written in base 10, whereas all the other numbers on this page have been written in base 13. Okay, before we move on any further, let's go ahead and take a look at some examples so that we can get an idea of what this function's doing. Okay, here we are. I have copied down our definition up here in the corner so that we can reference it. So let's go ahead and take a look at this first example. I'd like to know what C of x is, and x is equal to this number here. So we need to check and see if there's a tail of either type B or type C. So if I kind of follow along here, I can see at the end here, here's a B, here's an A, and then in the middle I have some digits from 0 through 9. And then here I have some digits from 0 through 9, and I'm going to assume, when I wrote these dots, I'm just assuming that the rest of these numbers are also between 0 and 9. Just as the creator of the example, I'm going to assume that these are all from 0 through 9. So in that case, this is a tail of type B. So the output of this is going to be, well, it's a tail of type B, which means the integer part is going to be formed by the numbers in here, so 0, 4. And the integer part of 0, 4 is just 4. That's how I'm going to interpret that. And then everything after the A is going to be the decimal part. So that's 1, 3, 3, and so on, whatever happens after that. So that's the output of the function for this input. Let's go ahead and try the next one. So for this one, I take a look and again see if it has a tail of type C or B. It does look like it has a tail of type C because I see a C here, an A here, and those are separated by numbers from 0 through 9. And then again, I'm going to assume that these are all from 0 through 9 as well, just as the creator of the example. Again, these are all from 0 through 9. Okay, so that means that c of x is going to be equal to, I look at this part of the function because it's a tail of type C. This is going to get mapped to negative 441.396, and so on. Let's go ahead and take a look at the final example. So for this one, x is 1/3. So we need to write this as a base 13 expansion. You may or may not have tried this before, but you can write a fraction like this in any base that you want using the division algorithm. And it turns out if you do, you will find that 1/3 in base 13 is actually equal to 0.444 repeating in base 13. So that's a fun little exercise to do if you have never done that before. But for now, we're just going to take this on faith. Let's take a look at what Conway's base 13 function does to this number. So we check to see if it has a tail of type B or C. Well, this one doesn't because it's just all 4s, so it's neither. So this is an example of the output being equal to 0. All right, excellent. So now that we have kind of a flavor of what this function does to a few inputs, we're going to go back to that original claim that we had about the base 13 function and try to sketch out a proof of it. All right, so here we are finally. I've copied down the claim that we made in the beginning of the video about Conway's base 13 function. So we said that Conway's base 13 function satisfies the intermediate value property and it's discontinuous at every real number. And we're going to sketch a proof of that now. In order to do this, we are going to use a small lemma that is pretty simple to prove, so we'll actually run through the proof real quick. The lemma is if f from R to R has the property that f of I is equal to R for any interval I, then f satisfies the intermediate value property and f is discontinuous at every real number. Okay, so what we're saying here is that if you have some function and it has this property where if you take a look at the image of any interval, you always get all real numbers. If you have a function with that property, then it automatically has to satisfy the intermediate value property and it has to be discontinuous at every real number. And what we're going to do after we prove this lemma is show that Conway's base 13 function actually has this property where it maps any interval at all to the real numbers. So let's go ahead and sketch a proof of this. So there are two things that we need to prove. The first thing we need to show is that it satisfies the intermediate value property. So let's go ahead and make some notes up here. Kind of section off a space up here. So the first thing that we need to show is that f satisfies the intermediate value property. So how do we do that? Well, if we just think about the picture, it is not too difficult. So if I have my xy plane here, the idea is if I pick an A and a B, and then I look at f of A and f of B, and I pick a y in here, then I need to find an x value in here such that f of x is equal to y. F of x equals y. That's what I need. So I need this x value. I need to show that that exists for any a and b and any y, like this. So let's go ahead and just say the following. Let a be less than b, and let y be between f of a and f of b. I need to show that this x value exists, but this is immediate from the property of the function that we are demanding right here. Because in particular, I know the image of this interval, a to b, is all real numbers. So that means y has to be in this image. So since the image of AB is R, then Y is in the image. And that's it, really, for the first part. So F satisfies this intermediate value property. Good. Alrighty. So for the second part, I need to show that f is discontinuous at every real number. And we're going to do this one by contradiction. So we're going to assume there exists an x such that f is continuous at x. And let's go ahead and draw a picture again up here with on our notes. So I'm saying there's an x value somewhere, and it's continuous at, or the function is continuous at this point. Let's say that that's f of x right there. Just looking at this property, though, that we've given this function, I can tell right away that this function cannot be continuous at x. And the reason I say that is because you can kind of think heuristically about what it means for a function to be continuous at a point, right? It means that if you change the input just slightly, the outputs should also change only just slightly, right? But that's not what's happening with a function like this. If I change the input just slightly and take a look at that interval, the set of outputs that I get is all real numbers. This function is going crazy in any interval that I pick. So this cannot be continuous. Let's go ahead and formalize that. So what I'm going to do is go ahead and pick an interval around f, so around f of x. Let's call this interval b. Now, since f is continuous, I should be able to find another interval a around x such that the image of a lands inside b. So I should be able to find an a such that f of a is a subset of b. Okay, this is the definition of continuity. If you're familiar with the epsilon delta definition of continuity, this is really all that is, just phrased a little bit differently. The idea is that this is my epsilon and this is my delta. So what I'm saying is that for any epsilon greater than 0, I should be able to find a delta greater than 0 such that if I get within delta of x, the output is within epsilon of f of x, right? So let's go ahead and write all of this down. We are going to let b be an interval containing f of x. I'm going to go ahead and scroll down here. Okay, so let b be an interval containing f of x. Since f is continuous at x, there exists an interval a containing x such that f of a is equal to b, or sorry, is a subset of b. So the image of a under f is a subset of b. But this is a contradiction. This cannot happen because we already know that the image of a is all real numbers. So this is a contradiction. Since f of a is equal to all real numbers. And so that means that f is not continuous at x. F is not continuous at x. And then that's it. That finishes the proof. Since x was arbitrary, that means that this function cannot be continuous anywhere. Okay, so let's go ahead and use this now to put the final piece of the puzzle in and prove our claim. Okay, so here we are. We're ready to finally tackle this claim. Now, I am just going to do a proof sketch here because writing out the details in full generality can get a little bit tedious. But my goal is to pick a really nice example that'll give you an idea of exactly how the full real argument would go. So if you're interested in filling it out, you should be able to fill out the formal proof from what we do here. So again, our claim is that Conway's base 13 function satisfies the intermediate value property and is discontinuous at every real number. Based on that lemma we just proved though, it's enough to show that the following property holds. So it's enough to show that C of I is equal to R, here C is Conway's base 13 function, for every interval I. So as long as we can show this, then we will have shown this claim based on that lemma. So let's just go ahead and sketch over here in the corner a quick picture as we have been doing. So in order to show this, what we will need to do is pick an A and a B, so some interval like this, and then given some value y, we need to find an x that's in our interval such that the point right here is on the function, so such that f of x is equal to y. Okay, now like I said, I'm not going to do this in full generality. It can get really tedious to write down, but let's pick a nice example that's going to show exactly how you can do this. So example. I'm going to go ahead and pick a specific example for y. Let's go ahead and say y is equal to negative 137.215, and then let's say some more digits after that. And then this is in base 10 right here. So this is in base 10. Okay, and then let's pick some values for our interval. So let's say that a is equal to, I'm going to go ahead and check my notes here because I have a particular example that I would like to use. So we'll say that a is 2.3a, 4, c, 1b, 2, and then some more digits onward that we don't really know what they are. Okay, and then b is going to be 2.3a, 7, b, 1, 5, a, c, and then some more digits after this. Okay, and so what we would need to do is find an x value. This is what we need to find. We need to find an x value that is in between these two numbers, a and b, and we need to show that the output is y equals negative 1.37.215, and so on. Okay, so the first thing to notice in this particular example that I chose, a lot of the first digits in a and b are the same as each other. So the first digit is a 2, second digit is a 3, and then an a, right? But at some point we see that this 4 is smaller than the corresponding digit in b, which is a 7. Now this will always happen at some point because a is smaller than b. This will always happen. Sometimes it'll be in the first digit, sometimes if the numbers are closer together, it won't be until a later digit like this, but it will always happen. And so what we're going to do is we're just going to copy down all of the digits that we see until we reach this first digit where the digit in A is smaller than the digit in B. And in that space, we are going to place the smaller digit. So by doing this, we automatically guarantee that x is smaller than b. No matter what we add on to x after this, we are still guaranteed that x is smaller than b. So that's the first thing that we needed. Good. We also need to make sure that x is larger than a. So to try and do that, we can place a c digit, because that's the largest digit we have access to, after this 4. Now, unfortunately, this doesn't guarantee that x is larger than a, because there's also a c here in a after the 4. But that's okay. I can just tack on another c after this. I can see that there is another digit c here in a once again. But that's okay. I can keep on doing this until eventually there will not be a c in a. And I know that eventually that will happen because, again, we said none of our representations are going to end in an infinite number of c's. So I just keep placing c's until I get a number that is greater than a. And so at this point, I can see that x is greater than a. So we have guaranteed, no matter what we put after this, that x is between a and b. Excellent. So now the last thing that we need is to make sure the output is equal to this up here. And in order to do that, I just need to put the proper tail on this number. And let me maybe do the tail in a different color. Since this number is negative, the output is negative, this is going to have to be a tail of type C, which means it will have to start with a C. And then I want the integer part to be 137, so I will follow that up with a 137. And then the decimal point is where the A should be in this tail of type C. And then to get these numbers in the output, I will just go ahead and tack these onto the end and continue on. Whatever the rest of these digits are, I will just keep on placing them. And that's about it. This is our number that we were seeking. And I think you can kind of see that no matter which A and B you pick, you can follow an algorithm that's either exactly this one or similar to this one to pick a number between your A and B. And then once you've done that, you just need to tack on the proper tail so that you get the output that you want. You should give it a try with a few more A's and B's to kind of get a feel for how this works. And if you're interested, try and fill out the formal proof. I will say there is still a little bit more to think about, and I will leave you with the following questions. So if you are going to write out the formal proof, these are going to be important to think about. So first question is, what if A is less than 0 and B is greater than 0? Is there any difference to the algorithm, or can you do it exactly like this? And what if A is less than 0 and B is less than 0? Can you still follow the same algorithm? Those are going to be important questions to think about. Maybe give that a try if you are interested. Pick some A and B values that are different than the ones that I have here and see if you can still work out the algorithm to see how to produce any Y value that you want. Okay, so I think that's about it for this video. I'll see you in the next one.